Hello and welcome back to the next chapter or the next installment of the Ray Tracer Challenge, where I implement this book or the tests and code from this book in Rust, a language which is kind of new to me and I've not used in any way before starting this.
Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun.
So we are not only implementing a ray tracer here, we are doing it in another language and learn it while we are going. So where have we stopped last time? The last time we took a look at the implementation of matrices, and we decided to utilize the basic array types of Rust here in order to implement those. So even though I've decided to do this and to simply name them here, I've come to the conclusion that we most likely want the implementation to be a struct anyway, to be clearer distinguished from the simple array, because otherwise we would implement all the functionality we are now adding and going to create for this on this specific array struct. So any array struct or any array constellation of this type would actually have those methods. It wouldn't be that bad, but as far as it goes Rust-wise, I think that it is not the way to go. So maybe we should simply do it a little bit different and just put a small encapsulation layer like a struct around those. And I've gone ahead and read up on the from trait, and that's actually what gave me the idea to do it maybe in another way. And yeah, let's take a look here, because that's a nice example. I guess that was it. So implementing the from trait is simply a way of telling Rust that we can actually convert from a specific type into our data structure. So we could implement the from trait with the data structure of our array, for example, here, and implement it for our struct then. And then we could simply put an array in there and store it. And the nice thing about this is that we automatically get from the compiler the other way around, the into. So we then essentially could simply put an array struct somewhere and just call the into on it, more or less converting / casting it into our structure, and Rust will automatically call the corresponding from trait and convert it. And that's actually something which looks quite interesting to me, and it kind of looks like the thing we want to do here. So let's go ahead and refactor this first, I guess. So what we are now going to do is, I think I'm going to rename those types, because I want some more specific typings for them. And then I'm going to... Do we actually need those types public? I don't think we need those types public now, but what we need here then is a public struct called matrix2f. And this public struct matrix2f should have something like data, which would be a matrix2f array then. So we are simply now holding this data inside the structure here, and I guess now we are implementing the implement from matrix 2f array for matrix 2f, and now how's this method? It's simply called from, and okay, so now we have this from method which takes our let's call it array, takes our array, which is a matrix 2f array, and returns self, essentially our matrix struct, and it does nothing more than initializing this thing with, oh, let's call it data actually, with data here. So this is actually our from trait, and no, of course, this indexing cannot work because we cannot access this, but we can, oh, we need to actually import use std convert from, and we need to implement the index operation. So use std ops index, and I want to implement index for matrix 2f then, and I actually need to read up on how this function is called. So we essentially need this type output here, definitely. So let's define that. So type output will be self, I guess. No, that's not right. Type output will be... Let's actually split this type definition up and do a matrix 2f array row, or matrix 2f row. Let's call it array row. So we are representing one row by it. So this is an array of arrays. So this actually would be this then, and we can do f64 2 here, so that we have this type separately, and now we are actually outputting this here for our index function. No, where did I open it? I opened it, here I did open it. So let's copy this implementation header here, the declaration. So index, we get self, and we get index, which is IDX. Is it a specific type, or is it a template, or what they are? Okay, it's sized. Okay, so interesting. Let's just tell the compiler to add the, oh no, IDX. So missing generics for traits. So we need to actually specify that. Let's take a look at an index Rust ops implementation. Let's just, is there an example? Pub trait. So here, nucleotide. So so we can actually actually implement indexing by anything we like. So I guess we are just doing it by usize in our case. So so then we have an fn called index here, which takes reference to self, and it takes an index, which is a usize, and it does return self output. So and then we should actually simply return the corresponding row. This should be quite easy because this is self data and then just get the corresponding index out of it. So expected let's see, maybe a slice is expected here and self has an anonymous lifetime, but it needs to satisfy a static lifetime requirement. Okay, so let's read up on that. So how are they doing it here? So they are returning a reference here, and are we returning a reference here? Okay, so we are returning now a reference to a slice of this data, which would be completely fine, I guess. I guess let's try it out. So this essentially should work again now, and it seems to me that it does, because the compiler is not complaining anymore, because now we can access the index on the structure and we get back our matrix here. So yeah, I guess this is the way to make it work. I'm now that we are consolidating all of this stuff inside struct, I'm thinking about merging all of the different matrices together, but for now I guess let's just do what we did for the other ones as well. So let's have here a 3F array row instead of this, and let's have here a matrix 4F array row instead of this inner declaration, and let's copy this there and just rename it and give it the corresponding size, and let's do this and give it the corresponding size. And now I guess we may mostly copy this for our 3F matrix, which will now mostly a complete, not only mostly, it will be essentially exactly the same. Can we somehow, I guess we could solve this copy and paste problem for by using a macro and have a macro that creates this stuff for us, but that's not, yeah, maybe that's something for another day. So let's copy it again for our matrix 4F stuff, and let's just matrix 3F with let's replace with matrix 4F here, and we should be good to go. So so yeah, actually now this should work, and we should have refactored everything so that it behaves exactly the same as it would. Wait a second, no. Now we are initializing simple arrays. We are initializing them from simple array structs. So this implementation is working, but we have to adapt those tests. So what we essentially really want to do here now is doing something like M is matrix 4F, and we simply call, I guess, from on it, and this should do the trick. Yeah, this should actually work. So let's replace all those, matrix 2f from, and we just put the array data in there, and it will encapsulate it nicely for us and give us a corresponding matrix. So we don't need the explicit type now anymore. I'm not sure we would have needed it before. So I guess we only had this there for I don't really even know why. So let's create another matrix here, and we had another matrix here, and that we don't actually had the type declaration here in those tests makes me quite sure that we wouldn't have needed them in the other ones as well. So let's just do it this way and have this way there. So the from is missing here. The from is missing here. Let's actually try one thing here. If I now say matrix 3f here, is it a 3f? Yeah, it is a 3f. And I do an into there. This should actually, yeah, and as you can see, this works. Because the compiler now knows that this is a matrix 3f, and it should properly transfer or create this type then there. But I would like this explicit one in this situation here more. So let's do this one, and let's do another matrix 3f here. Oh, there is a from missing again, and this is another one, matrix 3f from, and oh no, why did I do that? So matrix 3f from, and we are always initializing it from array data. We may be thinking about implementing a new for it as well, which maybe simply, I don't know what kind of data it would take. Maybe just the stream of values. Maybe this is a good idea. I have no idea. I actually kind of like it this way. So this is a 4f from, and we have another matrix 4f from array data here. Let's do it there. And how many tests did we write for this? 4f from this one, and matrix 4f from this one. And there we go. And there is another one. Oh yeah, the inequality test. We only had this for matrix 4f. Matrix 4f from. That's actually something which is kind of. I don't like this really. I don't really like this, so that we have all these different implementations for the different matrices, and I would really much simply like to kind of have this in one go. It would be kind of perfect if Rust would support template constants, so that we could do something like, wait a second, does Rust support template const values? Okay, first of all, let's run the tests and let's check. Oh, there is. We kind of made everything bad. Matrix 4f cannot be formatted using. Yeah, okay. I get that, because now we need to derive some things here. We need to. Come on, we need to derive debug, I guess. And then this should make it possible for us to actually, I guess I want all those. Let's reformat the order of those declarations. Let's put those at the top. And there we actually have the from implementations. Like let's move those together. So let's actually group them by implemented trait and not by struct. I'm not sure, I may resort this later on. So now we have all those traits and things and stuff together, which I'm not sure if I like, but let's see. So now let's run the tests again, and all tests are still passing. I like that. Do we have any warnings? Warning, build failed, wait, no. So no, yeah, okay, so this is actually working. So let's commit this. git CI, refactored matrices to utilize structs instead of raw arrays. So even though we did it transparently, I guess this is quite nice. So now let's just quickly, do we have Rust const template values or const generics? Let's create a to-do here, let's create a to-do here, to-do, maybe refactor to utilize one matrix struct in the future, const template per are const template parameters an option, question mark. So we don't actually need those in parentheses, so yeah, let's do it this way. And now let's git add source matrix, git CI, reordered functions or implementations by trait. So let's do it this way. I'm sorry, I have a little bit of a sore throat today, so might be coughing a little bit more than all the different other times. I'm already drinking something against it, but yeah. So let me exchange cups here. So okay, maybe we want to do this, but not now. So now we've actually implemented these base matrix stuff. So let's let's go on and implement the next thing. So the next thing we actually want to implement is multiplying of matrices. And a matrix can actually be multiplied with another matrix. And if you do this, you get a resulting matrix, which essentially would, if applied or multiplied with something else, would be the same as multiplying everything together. So you can essentially store different operations within one single matrix and apply them, for example, then to a vector or another matrix or something like that. So what we are mostly going to implement here is, if I'm not mistaken, is multiplying with only for the matrix 4x4 at the moment. At least this is what the tests say, because the 4x4 matrix will mostly the one we will be using. I'm not 100% sure where actually the 2x2 and 3x3 matrices are applied later on, because in the 3D rendering systems I've written before and another ray tracer I've maybe written 15-20 years ago, so I don't remember mostly of it. Then only the basic principles are in my mind still. I guess I only had 4x4 matrices, so which is kind of unintuitive. At first I implemented, of course, 3x3 matrices, because I thought, yeah, it's 3 dimensions, so I need 3-dimensional vectors and stuff, and so I only need 3x3, but it's the same reason we have 4-component points and 4-component vectors. It's a lot easier if you have 4x4 matrices and 4-component vectors and points with this marking of a point or a vector by the 0 or the 1 in the W component, simply because then essentially all of the different matrix multiplications work out. So we will see this later on. We will be creating matrices which transform, like rotate something or translate something, like a vector if they are applied to, so essentially moving them in space and rotating them. And that's exactly where you need a 4x4 matrix, because if you only have a 3x3 matrix, you can't incorporate the translation into the matrix. You would need to do it with a separate translation vector, and we don't want to do this. We want it inside the matrix, so we need a 4x4 matrix. But enough foreshadowing. Let's go ahead and implement the multiplication of matrices. So we now don't only need the index operation, but the multiplication operation, I guess, because we will essentially just implement that then. But first, of course, let's implement the corresponding test. As always. So fn, how's it called here? I guess it's just called multiplying two matrices. Multiplying two matrices. And let's make it 4x4. It isn't mentioned specifically here, so let's just implement it for now for 4x4s. So yeah, we got the following matrix. So we got let M1 is matrix for f from, and we got actually a 1, 2, 3, 4. Okay, that's very creative. 1, 2, 3, 4, followed by a what's this? 5, 6, 7, 8. 5, 6, 7, 8, followed by a 9, 8, 7, 6. Ah, okay, so we are going backwards now. 9, 8, 7, 6, followed by the last row, which is a 5, 4, 3, 2. Okay, 5, 4, 3, 2. So this is our first matrix. Did we do something wrong? Yeah, we actually forgot the surrounding array, which encapsulate all our rows. So, okay, the next matrix would be then... Okay, so now we have the let expected result will be a matrix for f from, and it essentially will be... Yeah, it gets a little tedious, doesn't it? So now we have all those values in here. We could actually do something like let actual result then would be M1 multiplied with M2. And of course this does not work out yet, but then we can do an assert fuzzy equals actual result with expected result. Let's do this. So cannot find function assert fuzzy equals in this scope. Ah, okay, I've forgot the exclamation mark because it's a macro. So yeah, of course, this does not work yet, but we can implement it, and this is exactly what we are going to do now. So where do we actually implement it? Let's do it here. Let's do it at the end of this. So we are going to implement the mul operation with another matrix for f for matrix for f. So I guess this was, we needed to define an output type, I guess, which was another matrix for f, because this were our result, and then we could implement the mul, which gets a self, and an other, which is a reference to a matrix for f, and it does return a self output. Expected struct matrix for f found wait, is it like that? But for now, how does matrix multiplication work? What you are essentially doing is you are taking, for each of the target elements, you are taking a whole row and a whole column from the input matrices. So if you are, for example, want to calculate the value, the target value in, let's say, row 3, index 2, you are going to take the whole row 3 of the first matrix of your multiplication and the whole column 2 of the second matrix within your calculation. And then you will multiply each of the values with the corresponding other. So on the one side you are wandering row-wise. So you will have inside the row the first column value, the second column value, the third, and so on. So you are wandering the row, and in the second matrix you are wandering the column, and you are multiplying the first value of the row with the first value of the column, and the second value of the row with the second value of the column, and so on. And you are just adding all of them up. And once you've done that, you should actually have, or you have the result for the specific cell you want to calculate in your target matrix. So so now let's think about how we can do this in some sort of loop. So we definitely would need to have, for something like we need to iterate over each row, which is for row in. So yeah, we actually can do this. Is this one, I guess it will be within this, so it will be inclusive, and we need to iterate for each column as well. So this will actually be for our target matrix. So let's just create an array here, which is, let's just say, let target, or we can simply say M, I guess. So let M, this will be of the type matrix 4F array. And do we need to initialize this one? Do we need to initialize it? Yeah, I guess we need. So maybe it would be a good thing to have a sort of new function which simply creates an empty matrix for us. Yeah, I would actually like that, so that we can then. So let's implement this. A matrix which is completely filled with zeros. So where would we implement those? I guess somewhere here. So let's do impl matrix 4F. And let's just have a pub fn new, and it will create a matrix 4F for us. Oh no. So, and it will be matrix 4F from, yeah, let's maybe do it. Okay, we need those here and there, and let's do it like this and make a comma here, do it like this, and just copy this up 4 times, and now we should actually have our new matrix 4F. And I would like to have this one for all of our matrix types then, even though we might not need it, but I would like to have it like this because it makes things kind of easier. So let's do this, and let's go with 2F as well, so that it is at least consistent here, I guess. So we are removing those again, and the last line, and there we go. now we have this implementation before implementing from. Okay, I kind of don't like this. So even though the Rust compiler seems to be absolutely fine with without having to forward declare anything. But yeah, okay, so now we should be able to, where were we with our implementation? There we were. So now we should be absolutely fine by simply saying here we want let mut m matrix for f new. So we will simply get an empty matrix, which is fine for me. So now we need to fill this matrix. So we need to fill up the row and the column. And the row and the column, yeah, and we of course want to return this one in the end. So, and the row and the column will actually be then, yeah, what will it be actually? It will always be, essentially what we would have here is we are going now through the through one row of the first column and one of the first matrix and one column of the second matrix. So what we are going here to do is we have self, and we always access the we are always accessing the row corresponding to the row we are currently going through, and putting and starting with 0 here and multiplying it with other, where we are taking the 0 row of the column we are currently. Just a second, this would not work. Cannot assign to data in an index of matrix for f. Cannot assign help. IndexMut is required to modify indexed content, but it is not implemented for matrix for f. Oh, okay. So the question here is now, do we want to do it this way? Do we want to allow it this way, or do we always want to initialize it directly from an array? Because I guess this would be possible, so that the matrix itself is kind of immutable. On the other hand, then our new implementation doesn't make a great deal of sense. So maybe we take a look at this IndexMut. IndexMut Rust. So how does this work? IndexMut. It's a okay. So it's a mutable self then, and it's then that's kind of interesting that we need to implement both, but in a way it makes sense. So let's implement this. Where is our index implementation? There it is. So let's, for now, just to check that if it's working, let's implement IndexMut for this one as well. So we are implementing IndexMut. So I guess we don't need this anymore. So IndexMut will need a mutable self then, and it should output a mutable self, and this should, we should import it, of course, like here, IndexMut. And mismatched types differ in mutability node. Expected mutable reference. So there, yeah, let's output a mutable reference, and now let's just check now if our implementation would be okay with that. So now our implementation is satisfied. So yeah, I guess we will actually do this for all of them, just to have a little peace of mind. The amount of boilerplate I'm now creating here actually is astonishing. I could simply have used the base array structures for this. Until now it would have worked flawlessly, I guess. maybe my refactoring wasn't the best thing to do, actually. It is, yeah, I don't know. It's a lot of, oh no, this is 2F and this is 3F. It's a lot of stuff that is only there to satisfy all this compiler needs now, which would have worked automatically before. But okay, let's go on with this. So we have this row and other column, and now what we essentially want is we want a plus here, and yeah, I know it will go, oops, it will go absolutely bonkers once I reformat it, but I want to make it easier for myself to copy this, because we need to do this 4 times. So now we will have this row here, and here the column 1, and this is 2, and this is 2, and this is 3, and this is 3. And actually, if I now, oh, that's not as, oh, I'm sorry. This is not as broken as I sort of thought it would be. So, and maybe we should make it more explicit here, because just having the little m there I don't like. So now we have that. Yeah, I guess we run our tests and see cargo test matrix. Let's check if this is working. Okay, they failed. Panicked at asserting fuzzy equality. Matrix 4F data. I guess this is exclusive then. Let's check. I guess I've seen this already. I've even used it already somewhere, but okay, let's just do this for 0 to 4. So we just need to remember that this syntax is exclusive, which I kind of find a little bit, yeah, okay, it's so that you can easily say something like go from 0 to the length of this thing, but yeah. Okay, so yeah, now it's passing. So we have properly implemented matrix multiplication. So let's commit this. Git add source matrix, git ci, implemented matrix multiplication for 4x4 matrices. There we go. So that's kind of nice. So what is the next thing? Yeah, the next thing actually is the identity matrix. The identity matrix is a funny thing. So with each multiplication, we know we have a sort of, or with a lot of multiplications, we know with the usual ones, with the, for example, natural numbers or rational numbers and stuff like that, we always have an element which is the identity, which is if another value is multiplied with it, the same value will be the result again. And with matrices, there is actually more or less the same thing. There is a matrix. If you multiply with this matrix, you get the exact same result matrix as you put in as a multiplier. So no, if you use it as a multiplier, what is it, multiplicand? I'm not sure about the terms in English. So let's just write a test for that. So multiplying a matrix by the identity matrix is the test name. Multiplying, let's call it 4x4 matrix by the identity matrix. We should actually have an assert fuzzy equals actual result, expected result. Yeah, and we still don't have this identity function, so let's implement this one here somewhere around about here. So pub fn, so we could actually copy this one. Of course, we need a lot of those. So the identity matrix is actually a matrix where the diagonal is consisting of the value 1. So this is actually the identity matrix. Identity. And if you are thinking about how matrix multiplication works, it at least makes it makes a lot of sense, because always at all the positions here which correspond to this, all of the factors within the multiplication. Let's take a look at how this is working is implemented again. You will always have for each of those fields, there will only one equation of this will have a 1 in it, essentially. So all the others will be 0, and so you will simply be having the value there that's already there, because the only one which has a 1 there and not a multiplication by 0 is the one at the exact position where you are within your target matrix. So essentially this is why this works. So let's take a look. Use of moved, M1 value used here after move. So yeah, we actually moved M1 into the expected result, didn't we? And now M1 is expected result and not. Can we do it this way? Cannot move out of M1 because it is borrowed move out of M1 occurs here. Yeah, that's exactly what I feared. In order to do a multiplication, we need to move the value. Couldn't we just? That's kind of what I feared when implementing it. Like, where is it? Implementing the mul operation here. So where is it? There it is. What I really much would like more is something like this. And this. Maybe this is not needed, but can I have it this way? Yeah, I don't like that the self is moved in here. So let's see if we can actually implement this for AND matrix to F. And so yeah, this should actually already do it, shouldn't it? So yeah, but now we need, of course, to do this, don't we? Okay. So do we want it like this, or do we want to copy it actually? Let me check one thing. If we would have implemented it as simple arrays, do arrays have copy semantics Rust? If I want to know if an array has the copy semantic. Arrays of any size implement the following traits if the element type allows it. Okay, so if we would have used a simple array, it would actually have been copied. Maybe we should then really just have this structs implement copy and clone. So I have no idea if this is a best practice or a bad practice, or if we are actually in my guess is that this will definitely have a performance impact, and ray tracing is a very performance hungry operation. So, but maybe we will do it this way now, and then if we have a real ray tracer later on, we can start profiling it to get to know profiling tools within Rust as well. We could do this after we've implemented all this. So just to just to get to know that, and then make it fast. First, let's make it work, and then let's make it fast. So now we need to change this mul implementation again, of course. At least it's really nice to know that we can do this, and now we know how. And I like that because we've learned something new again. So where were we? We implemented the identity matrix. There we are. So now let's run those tests again, and they work. So we've actually implemented the identity matrix. And this call here actually now copies the struct, which I guess is right, but the moment we are giving it to some function, then we would always copy it there and not simply transfer its ownership there. But yeah. I've actually, as I said, forgotten something in this book, because it does another thing first here, is before implementing the identity matrix, we actually further implement all this kind of multiplication stuff. Because we are not only implementing matrix by matrix multiplication, we are implementing multiplication of a matrix with a tuple. And yeah, essentially this is possible as well. The result of a matrix multiplied by a tuple will then be the same dimension as the tuple. So we can easily implement this. Do we write the test first? Yeah, let's write the test first. So let's actually put it at the correct position. Oh no, did we commit this? Source matrix. So I guess yeah, git sc, git add source matrix, git ci implemented identity matrix. So let's do it like this. And now we will add the multiplication here for a tuple. Yeah, I guess then this would be m multiplied by v, which we haven't implemented yet, and then we make a fuzzy equality between actual result and expected result, as always. So let's mismatch types, expected structs, yeah. Yes, of course, because we only have one multiplication implemented, but we can implement it, I hope, for more than one type. So where did we implement our multiplication? There it is. So now let's implement the multiplication with a tuple for matrix for f. So type output will be then no, it will be a tuple, and fn mul will mul will be self and other is a tuple, and we will return self output, I guess. Cannot find tuple in this scope. Oh, should have written it like this. So, see, and now if we are treating the tuple like a kind of a miniature matrix, so it always only has one column. So what we are actually doing is we are now iterating the rows. So row in 0, 4 for exclusive, we are essentially we need to, I guess we are creating a new tuple here, like let tuple equal tuple new, but what values do we put in there? Maybe just zeros. We will definitely override all of them, but I did something wrong there. So question here is now, I want this mutable, of course, and now I will do tuple so tuple no, wait. I guess we will just spill it out here directly. So let's do it. Tuple new, and it will be the following. For the x, it will be a multiplication of the following: self, which is the matrix, row 0, index 0 multiplied with other x. So the first one there, plus, let's copy this a certain amount of times, 4 times to be precise, because we need it 4 times. So we have this, and then we will stay in the same, wait a second, we will stay in the same row but advance the column. So we will do this, and we will actually have this here, z, w, and this will be the first, and then we will have the same thing actually for the second row, which will be the second row of our result, and we will have it for this third row, and we will have it for the fourth row. So yeah, even though this is not, we could have done it with a loop or something like that, but as we cannot address those values easily by index, I guess it is okay to do it this way. So let's run the tests then. And we are failing. What did we do wrong? It seems to me we did something wrong with the calculation. What did we do wrong? Tuple 14, 22, 33, 32, and we expected 18, 24, 33, 0. So, wait a second, 0? Oh, I used a vector, didn't I? Yeah, I should have used a point, even though this should not make a difference at all, but let's change this up, because the test in the book explicitly tells us to do it, to create a point. So let me check if this is right. 18, 24, 33, 1. Yeah, so it's a point. So let's change this multiplied by a, yeah, in the book it says tuple actually. So I guess the author wanted a value other than 0 within the W component to see if we did something wrong with calculation. So yeah, let's check this out. We now have this. Okay, let's rerun this, and now the tests are okay. But this doesn't really make sense, because the matrix as we had it there shouldn't have interacted with the, oh yeah, it should have, because essentially the where is it, if this column here, the last column, this one, if those values here would have been 0, it should be exactly the same regardless of what the fourth component of our tuple would have been. So as we have a point, yeah, that's like the book defined it, and that's working out. So I guess we will commit that. Add source matrix git ci implemented matrix by tuple multiplication. So yeah, so the next thing we are going to do are different further matrix operations, like implementing the transpose of a matrix, and then we will actually go ahead and implement all the steps needed to create the inversion or inverted matrix to a matrix, which is actually sort of, yeah, the inverse operation, but we will get to that once we do this. For now, I will take a short break, and thanks for watching me again, doing further implementation stuff on the Ray Tracer challenge, which I very much like. The book is really great, even though we haven't gotten that far yet. So, but we are coming along. I'm learning Rust, and we all together have fun seeing me struggle while I do this. And yeah, thanks for watching this. If you like it, please give me a thumbs up, and please subscribe if you want to be notified when the next installment of this series is coming out, or other stuff I do on the channel. So yeah, thanks, and see you next time. Bye!